Okay, the ballot measure question here. I would think it would be very likely that we could see some version of this or something like this on the actual exam. It hits a lot of things that are, I think, pretty important to understanding the major parts of the course. So the first part asks, what's the probability that the proportion of voters in sample of region A who support the ballot measure is greater than 0.5? So hopefully you recognize this when it says what's the probability. Hopefully you recognize this as a normal CDF deal. Otherwise it would be pretty hard to come up with any kind of way to calculate this probability. So they tell us that it should be centered at 0.47 on average. That's where all the p-hats are. Now we know that if that's the true proportion, it doesn't mean that every time we take a sample of whatever size, we're going to get 0.47, all right? There's a chance that our sample, depending on its size and everything else, could be greater than 50%, and that's what they're asking us, okay? Now, this is huge, right? The sample size is 500, all right? So this is a normal CDF. Okay, obviously we're going from 0.5 as our lower limit. We could just say 1 as our upper. The mean is easy, it's 0.47, okay? How do we get that standard deviation? Well, it's on your formula sheet, okay? On the formula sheet, if I switch over to my formula sheet right now, I'll lose all my ink, so I'm not going to, but I'll jump back to it in a second if that's helpful. But we have this formula where we have P times 1 minus P, which would be 0.53, divided by 500. We've seen this many, many times over the past couple of months in class. So that would be what I want to use for my standard deviation, right? 0.47 times 0.53 divided by 500, and it's the whole deal is under that radical. So like I was saying before, it's just this formula right here, sample proportions, right? 0.47 times 0.53 divided by 500. So let's hash that out on the calculator. We have second vars for our normal CDF, always CDF, right? For binomial, it could be PDF or CDF. So our lower limit was 0.5. Our upper limit just needs to be pretty high at 1. The mean of those sample proportions, they told us, lives at 0.47. And then our standard deviation, this is where we needed our formula from our formula sheet, 0.47 times 0.53, and we would divide by 500. Just enter that. So I get 0.089. Okay, in the next part, they tell us to describe a sampling distribution where we're combining the two random variables, right? So describe the sampling distribution of the difference in proportions region B minus region A. So one part of this is going to be real easy. They tell us region B is centered around 0.51. Okay, so you want to try to write in complete sentences. I'm not going to type this out or write it with my pen here. It's just not gonna. It's going to take up too much space. But the distribution of those differences, right? Like if I go into region A and take many, many samples, and region B and take many, many samples, and every time I get a proportion, I subtract them. Well, then on average, where would I expect those differences in p-hats to be if I do B minus A? I'd expect them to be at 0.51 minus 0.47. I'd expect them to be centered around 0.04. Okay, so I would say the distribution of those differences in sample proportions would be centered at a difference of 0.04. Okay, the spread or the standard deviation, that's just going to be our first standard deviation, right? Remember our rule, right? There's no rule for standard deviation. The rule is for variances. So 0.47 times 0.53 divided by 500. And then I can add that variance to 0.51 times 0.49 divided by 500. That's the combined variance. Well, my rule is that variance is always add, so I would have to take the square root of that. Okay, and that would be their differences. What would be their shape, right? Center, shape, and spread. So we took care of center right here. We talked about spread, and the shape is going to be normal because 0.47 times 500 is greater than 10. 0.53 times 500 greater than 10. 0.51 times 500 greater than 10. 0.49 times 500 greater than 10. So you want to make sure you talk about center, shape, and spread, and give justification for each of those. Okay, so for spread, let me correct that. I just looked back up there and saw. So region A, we still have 0.47 times 0.53. And I just scrolled back up. I couldn't see it on my screen at the time. But region B, they're only taking a sample of 400. So that'd be 0.51 times 0.49 divided by 400. Sorry about that. Okay, so my standard deviation is going to be that. And then for shape, it's definitely going to be 0.51 times 400. All of those are greater than 10, so we're okay on that. Okay, and then finally for the last part, what's the probability that the two samples will differ by more than 0.05? This is kind of tricky, right? So we expect their difference to be 0.04, right? Now, they could differ by 0.05 up here. Okay, when I subtract them, and this is obviously the more likely thing that can happen. If I do region B minus region A, that's more likely to happen. But it's also possible, right, that their difference is down here at negative 0.05. Like, you know, think about what if region A happens to be bigger than region B in a particular sample, right? It's possible. It's not likely, but it's possible, so we have to consider that, okay? So the easiest way, in my opinion, to get this area, I would get the area that I don't need, the white area, and just subtract it from 1. So what this would look like for me is I would say normal CDF my pen would cooperate with me. And let's go from negative 0.05 to 0.05. We put 0.04 in the middle. And recall what our standard deviation is going to be. It's that big formula I just had up here, 0.47 times 0.53 divided by 500. Add our variances, 0.51 times 0.49 divided by 400. And we take the square root of that. Okay, so we'll normal CDF that, and we ought to get the probability that they differ by more than 0.05.